This is lovely opportunity to talk about our work. As Patrick said, this is joint work with Philipp Strack, and let me jump right into what this paper is about. All right. So let's take like a classic question in sort of Econ 101, which is, you have a good, and that good causes a positive or a negative externality. Let's just think of a negative externality. How should we regulate the consumption of that good? Think of something like pollution or congestion. And if you've taken Econ 101 and you're a well-trained economist, your Pavlovian response will be to say something like Pigouvian taxation. So markets will be inefficient. You should charge a tax that equals the monetary value of the externality cost, and that will cause the person who's consuming it to take into account the externality they're causing on society, and voila, efficiency will be restored. And this is what we, sort of teach as economists. But then when you go to just about any other social science or any other any regulator, they will almost uniformly tell you that they don't like Pigouvian taxes. They don't get used a lot in practice, and the common intuition is that Pigouvian taxes disproportionately hurt the poor. Conversely, regulators often like things like non-market solutions, things that we don't think of as things that we as economists would refer to as non-market solutions. So things like consumption caps, things like quotas. And this paper is about understanding whether or when these things make sense and why regulators might have a case when they say Pigouvian taxes disproportionately hurt the poor. So our question takes as a given, our paper takes as a given that the society in which you're trying to regulate the externality might be unequal. That is, people might have different values for money, or equivalently, the social planner might have a preference for redistribution or place different weight on giving a dollar to different agents. We're going to start with a very sort of classic baseline model, which is there's going to be a continuum of agents who are going to differ in three components. They're going to differ in their value for consumption of the good, their value for money, and how much they dislike the externality. And all three of these components are going to be private to them. There's going to be a distribution of types that's exogenously given and standard linear utilities. So our baseline model is going to be very simple indeed. And within that baseline model, we're going to show you a couple of straightforward results. So first, what we're going to show you is a sort of new spin on Pigouvian taxation, which is that in this, we sort of define what is Pigouvian taxation in this setting that we've written down, and that turns out to be just charge a linear tax on consumption, which equals the dollar value of the marginal social cost of my consuming a little bit extra, and then redistribute these proceeds equally across people. We're going to show you that in this setting, the Pigouvian tax is the unique incentive-compatible mechanism that can implement a Pareto-efficient outcome. So there is no other incentive-compatible budget-balanced mechanism, feasible mechanism that can implement a Pareto-efficient outcome. On the other hand, as we know, for any given Pareto-efficient outcome, there are corresponding Pareto weights, and the corresponding Pareto weights for the mechanism for the Pigouvian tax as thus defined is that it puts higher weights on richer agents. That is to say that agents who have a lower value for money get higher weights. That we interpret as maybe a formal reason why people have the sort of intuition that they do, that that Pigouvian taxation unfairly burdens the poor, or and so on and so forth. We're then going to go ahead and say, okay, well, if Pigouvian taxation is the only mechanism that you have that gets you to Pareto efficiency, what can you do if you have a given objective and you want to do something else? So we're going to take two objectives. One of them is the standard utilitarian objective. The other is a novel objective that we use in mechanism design a lot, but doesn't get used as much in the context of regulation. And we're going to derive the optimal mechanism under these objectives. We'll show you that all sorts of things that we might previously have called non-market solutions, things like consumption caps, quotas, prohibition, and so on, become optimal mechanisms in under these objectives, taking seriously the idea that society might have inequality, wealth inequality. And we're going to give you it's not just that we're going to do a mechanism design exercise, we'll also identify flexible distribution forms, in particular the log normal, where the associated mechanism design problem is very tractable analytically, and you can do a whole bunch of rich comparative statics. Now, like I said, the baseline linear model is sort of meant to get us off the ground, and but everything in that is exogenously given or exogenously given. In particular, the value for money is exogenously given. But one of the hopes or conceits of this paper is that hopefully we can be somewhere at the intersection between the large literature on mechanism design and the large literature on optimal taxation, so we can bring mechanism design tools further into thinking about the taxation and regulation of externalities. And the public finance literature has a very different sort of way of thinking of the world, in which case, for example, traditionally, those classes of models think of agents, instead of having some exogenously given value for money, they often have agents have a exogenously given productivity, and they choose how much to work and how much income to have as a function of the tax rate that they're facing. So we're going to, towards the end of this talk, we're going to extend the model out into a richer nonlinear model where agents have heterogeneous consumption value and heterogeneous productivity, and that these agents will face an income tax that depends only on how much money they make, and a sales tax that depends only on how much they choose to consume. Given the income tax schedule and the sales tax schedule that they face, agents will choose how much to work and how much to consume. We're going to show that nevertheless, in this richer model, our previous characterization will still be valid. But now, of course, the value for money will be endogenously determined. So all our previous insights will continue to go through in this richer public finance setting. All right. So what should you take away from all this? So the first thing we want you to take away is that there's obviously a large literature in the public finance that also thinks about the taxation of externalities or closely related internalities, that is sin goods. And most of these papers entirely use a first order approach. So they take the planner's problem, they fold the incentive compatibility constraint to the objective, and solve for the tax, assuming that the relaxed optimal satisfies some sort of appropriate monotonicity constraints that come from the incentive constraints. What we're going to show you is that this latter assumption is not true in general in these sorts of settings. Even under very natural regularity assumptions, monotonicity constraints can bind at the optimal. So in general, in sort of even in very, very regularized settings, you need to do ironing, and we'll show you how you can do that. And sort of part of, I think, the contribution of this paper is to make clear this point that you shouldn't just ignore these monotonicity constraints, and you really should do a full mechanism design style approach rather than a first order approach. Second sort of takeaway from this paper is the literature on redistribution starting from Atkinson and Stiglitz. So the classic result of Atkinson and Stiglitz show that even if the planner might be interested in redistribution, the planner should not use commodity taxes to implement any sort of redistributory motive. The idea being that the commodity tax will in general be too distortionary to be optimal, and sort of their result or their sort of organizing principle was that you should use income taxes for redistribution. We show that this is due to a very specific assumption in their setting, which is that agents have homogeneous preferences over consumption. And in general, with heterogeneous preferences, a commodity tax can be optimal. There's also a related paper by Doligalskier Dvorak, Akbarpur, and Commoners that's out recently, making a similar comment on Atkinson and Stiglitz. There's a large literature. We touch upon both sort of the literatures on mechanism design, especially in the presence of externalities or in the presence of inequality, people with different values for money, and large literatures, obviously, in the realm of public finance and taxation. I'm going to skip over these. Hopefully, there's the link to the paper that is being circulated, and you can see how what these papers are and connect. Unless there are further questions, I'd like to jump into the actual talk and model. So those will be my still too long introductory remarks. I'll take a pause for a second just in case there are questions. All right. Okay. So let's start with the model. Like I said, our baseline model is meant to be very canonical. So we're going to have a mass of agents, and each of these agents is going to have a three-dimensional type, three numbers. Theta V is going to represent their value for the good. Theta D is going to represent their disutility from the externality, and theta T is going to represent their value for money. So the utility of an agent from consuming X when they make a payment of T, and when the total consumption in society is X bar, is going to be given by this straightforward linear functional form. Theta V times V of X. So theta V, your value for the good, times some common function V that transforms your the amount you consume. Then you're going to suffer a disutility from the externality. So theta D times some function D of the total amount that is consumed in society. And then depending on your value for money, you'll suffer a disutility for the amount you transfer out. Okay, so this is the agent's utility. We're going to make a few simple normalizing assumptions. So the first is, of course, you could multiply everyone's utility by everyone's components by 5, and you still have the same thing. So we're just going to assume that this is normalized so that the average value for money in society is 1. Okay, so this is just a straightforward normalization. And the second thing we're going to assume so that theta V is interpretable is that we'll assume that V prime of 0 is 1. So theta V represents your marginal utility for your first unit of consumption. We'll assume that all 3 of these components are private info. That is, each agent privately knows how much they value the good, how much they value, how much they dislike externality, and what is their disutility from transfers. And this could be, for example, that income is unobserved by the designer, or equivalently, that the space of mechanisms that you're allowed don't let you condition on theta T. You can, so those two things are, from our point of view, equivalent, and depending on where we are in the paper, 1 or 2 might be the more reasonable way to think about it. Components of theta can be correlated, so we're not making any independence assumption except in specific parts of the paper. We're going to assume the continuum model to focus on a small agent, but approximate insights will carry over to a model with a large number of, a large but finite number of agents who are all individually small. And as I said, this additive form is for analytical convenience. We'll have a concave utility function later in the paper. Okay. So what is the planner's problem? Well, you can, by the revelation principle, you can think of the planner as basically picking how much an agent should consume as a function of their type, theta, and how much that agent should pay, t, as a function of their type, theta. We'll carry around one more piece of notation, x bar, which is just the integral of x. So it's the total consumption, the total amount of externality generated in society. The planner will face 2 constraints. So the first is the standard incentive compatibility constraint. Because these components of type are private, every agent should get at least as much utility by reporting their type truthfully as by misreporting their type. Okay, so that's the standard incentive compatibility constraint. The second constraint is a budget feasibility constraint. The good is whatever whatever this activity is being, we're assuming it's going to be manufactured at a cost of kappa per unit. That's some given number. And the total transfers to the planner have to be such that the planner raises at least as much money as the amount it costs to finance the total amount of consumption in society. This could be zero for certain kinds of activity, but for others, we're just assuming a linear cost. And there's no other revenue goal for the planner. It's just a goal to make sure that they can fund the amount that people are consuming. Now, what are possible objectives for the planner? So these are the constraints. We'll think of three objectives for the planner. The first is the standard Pareto efficiency. So a function x and t, that is how much each type consumes and how much they pay, is Pareto efficient. If you can't find another budget feasible x prime and t prime in which every agent is weakly better off and at least a positive measure of agents is strictly better off. So that's standard Pareto efficiency for this setting. The utilitarian objective is also standard. It's just maximize the total utility of agents from the mechanism. So sum it all up and ask and try and maximize that. The allocative objective is an objective we use a lot in mechanism design, but one that doesn't get considered, like I told you earlier, in the context of public finance. And it says, look, in the utilitarian setting, you kind of can give yourself utility as a planner by just taking money from a agent with a lower value for money and giving that money to an agent with a higher value for money. Whether or not you can do it this incentive compatibly is a different question, but you can achieve this. That might not be particularly normatively appealing. So the allocative objective says, look, you are in a society where there is inequality, but you don't want to directly give yourself props as a planner if you're redistributing money. Instead, what you want to do is you want to maximize the net social surplus generated by the allocation. You're not taking into account the welfare impacts of the transfers and who is making them, but you are mindful of the fact via the incentive constraints that there is inequality. Okay, so this is what we call the allocative objective or the narrow allocative objective. It's intentionally a narrow notion that only cares about the good and its externality, as I said before, whereas the utilitarian objective takes into account the gains from redistribution. There's this philosophical question of whether a planner should account for redistributive gains. So, for example, when in 2019, when the US Democrats proposed the Green New Deal, they proposed a bunch of stuff that was sort of climate policy related. And then they proposed a bunch of stuff that we will take some of the proceeds from the taxation that we're doing on climate activity, and we'll do a bunch of stuff that is explicitly redistributive, pay for schools in poorer areas, things like that. And one of the criticisms that came up among many was that you should really do these two things separately. So the climate protection element should be the climate protection element, and then separately we can talk about redistribution if you want. The US Republicans sponsored a resolution in the House criticizing it. When we started writing this paper, we noted this resolution. It was by a then unknown congressman who is now Speaker of the House. So that's a funny side story. We're not going to take a stance on how much, which of these objectives is right. It depends on the planner. We'll just characterize the optimal for any linear combination of allocative and utilitarian objectives. All right. So let's get to the results. So the first is, in this setting, what is a Pigouvian tax? And a Pigouvian tax is, if you sort of write down the problem correctly, the Pigouvian tax charges agents the marginal monetary value of the externality. So basically, it places a tax of the expectation of theta d over theta t across the population and charges that tax per unit of consumption. So your transfer to the principal will be kappa, the price of the underlying cost of production of the good, plus the externality, this plus this tax, times the amount that you choose to consume. Now, the planner has all this extra money. The planner is gathering this much when you consume this much. So what does the planner do with the extra money? The planner, as you recall, had no revenue objective. So the planner has to redistribute this money to the agents. And the planner, because of incentive compatibility, can't give the money in any other way. So it just redistributes an equal amount to every agent, which is this. So this is the transfer that you as an agent get as a or have to make as a function of consuming this much. Now, note that, of course, this takes into account the or the taxation equals the marginal monetary value of the externality, which is different from the marginal from the average disutility. And here's the first theorem, straightforward. It says the following three things are equivalent. So first, X naught T naught, the mechanism described previously, is the Pigouvian tax with equal redistribution. So it's X naught T naught is the mechanism I described on the previous slide. It says that's equivalent to a mechanism that is incentive compatible and Pareto efficient. So if you want incentive compatibility and Pareto efficiency, you only have in this setting the Pigouvian tax with equal redistribution available to you. And the third is that this mechanism is optimal for a planner who places a Pareto weight 1 over theta t on an agent of type theta. That is to say that an agent with a higher value for money gets a lower Pareto weight and vice versa. Equivalently, this mechanism, the Pigouvian tax with equal redistribution, is optimal for a planner that wants to maximize this objective function subject to the budget constraint and incentive compatibility. So the third part is what we thought was surprising in the sense that it shed some light on why people might say that Pigouvian taxation favors the rich or disadvantages the poor. And the proof is fairly straightforward, which is to say that if this type, if you think about this type with theta v, theta d, and theta t, because a linear transformation doesn't matter, it has the same preferences as this type. Now, if you consider an economy where types are distributed according to these transform types, where everyone has theta t of 1, and you transform their value for money and disutility for the good appropriately, disutility for externality appropriately, this is a standard quasi-linear economy. And by your usual results in quasi-linear settings, so you open up Mascolel, Winston, and Green, or Jale and Rennie, and you get back that the Pigouvian tax with the equal redistribution results in Pareto efficiency. Uniqueness follows from the uniqueness of incentive-compatible payments given an allocation. And quasi-linearity implies that Pareto efficiency is equivalent to utilitarian efficiency. So when you're quasi-linear, the Pareto efficient frontier is on a single line. So that's sort of the sketch of the proof. And we have a little more interpretation. But the main thing is that if the planner wishes to optimize for different welfare weights than this 1 over theta t welfare weight, or any other objective function, then they'll have to give up either linearity of the taxes, or they have to give up Pareto efficiency. And that's precisely what we do next. All right. So now you have this planner's problem. The planner wants to maximize some weighted sum of allocative and utilitarian objectives, subject to the two constraints, the budget constraint and the IC constraint. And now you can start cranking the standard mechanism design wheel to get some results. So the first thing you can do is you can define this variable rho, we'll call it rho, which is the ratio of theta v, the value for consumption, divided by theta t, the disutility of transfer. And I'll call this rho the willingness to pay. Given the distribution of theta v and theta t, the corresponding joint distribution as given by capital F, you'll induce a distribution on rho. We'll denote that induced distribution H, and there'll be, assuming that capital F has a density, this will have a corresponding density, which I'll denote by little h. So now you have the standardish sort of results that a mechanism is incentive compatible if and only if the mechanism almost surely depends only on rho, only on the willingness to pay. So you can only screen agents on their willingness to pay. The allocation has to be non-decreasing in rho. Higher willingness to pay agents have to get more of the good. And the transfer as a function of this willingness to pay has to satisfy the standard sort of Myasonian rent extraction formula. Without loss, the planner should not collect any more money than they absolutely need. That is to say that the total transfer among agents should equal the cost times the total amount of consumption in society. And in particular, that means that you can use this to pin down this T of zero, the constant in the in the transfer formula. You can plug through this, and you can say that you get a standard virtual value type thing, which is to say that the welfare of the designer in a incentive compatible mechanism XT is given by this thing over here. What is this thing? It's a virtual surplus minus the disutility of the externality and minus the cost of production. So what is the what is this virtual value? This is the formula for the virtual value. It looks a little daunting, but it actually has a little bit of economics. So let's talk about this for a couple of minutes. There are three components to the virtual value. Note that recall that alpha was the value you placed on the allocative component. So that's the alpha over here. What is A? Well, look, when you think of yourself, or when you think of the allocative value that you get, you're going to allocate agents according to their willingness to pay Z, but you care about how much value those agents have for consumption, which is theta V. So this captures the fact that when you allocate an agent with willingness to pay Z, you're actually collecting the conditional expected value of consumption that those agents have. And that's why this is the corresponding virtual value component for which is coming from the allocative part of your utility. Now let's talk about the utilitarian part of your utility. So two things are happening. First, this is the standard revenue. Oh, sorry. This component B is the standard revenue raised by a willingness to pay of type Z, the standard Myasonian virtual value. Why is this coming into your utilitarian preferences? Well, all the money that you raise as a utilitarian planner, you're going to then redistribute to agents. So when you raise an additional dollar, you're going to give out that additional dollar to agents. And remember, we normalize the value of money in society to 1. So this is this component over here. What's the last component? If you give an agent with willingness to pay Z a little bit more of the good, by standard mechanism design ideas, that means that agents with willingness to pay higher than Z collect a little bit more information rent. The information rent is dollar denominated. So what happens is you also, as a utilitarian planner, collect uh, this quantity of information rent times this dollar value of information rent times the expected dollar value of agents who have a willingness to pay higher than Z, that many, planner utils worth of additional value. So this is the virtual value. You might need to iron. If you need to iron, then you do the standard ironing thing. But once you do that, you've got the ironed virtual value, you can just solve pointwise for the optimal allocation, which is willingness to pay by willingness to pay. Take the ironed virtual surplus minus the cost and pick the optimal allocation for that type, and pick then you can calculate out the transfer and the redistributive part from the budget balance. So that's this theorem over here. Few things to note. First, note from here that the amount an agent consumes depends only on the average disutility from consumption in society. That is to say that the joint distribution of disutility and disutility from transfer and disutility from externality has no effect on the optimal mechanism for the planner. Only the average, the expected disutility matters. Whereas if you recall, the Pigouvian tax depended specifically on the expectation of theta d by theta t, that is to say that the joint distribution mattered. So, ceteris paribus, if rich people have higher disutility, the Pigouvian tax is higher because the monetary value of the disutility has gone up. On the other hand, the allocative or utilitarian objective optimal mechanism for the planner will stay the same. Okay. Now, you might ask, how do these mechanisms differ from Pigou? And in the paper, we sort of describe, I'll go through this quickly. So we make a couple of simplifying assumptions. Let's not go over what they are. But under those simplifying assumptions, just enough simplifying assumptions so that we have some control. If you consider a planner with a purely allocative objective, then there exists some cutoff rho prime such that the Pigouvian tax will give the good more, or the Pigouvian mechanism will give the good more than the optimal mechanism for the allocative planner for all types with willingness to pay above this cutoff. And conversely, the allocative will give the good, the allocative optimal would give the good more than the Pigouvian for all types below this cutoff. So what's kind of the story here? Think of, for instance, people with very high willingness to pay. Our sort of simplifying regularizing conditions is there are two reasons one might have a high willingness to pay. One reason for that is that you might have a high value for the good. The other is just that you have very low value for money. Of course, the allocative planner wants to allocate the first and not allocate the second, but they can't screen, so they have to depend on the average. The simple the assumptions that we make, the regularity assumptions that we're making, say that on average the planner sort of arbitrarily high willingness to pay comes from people who are more likely than not just people with very low value for money. So the allocative efficient mechanism for the planner would like to actually give less of the good to these people than people with than the Pigouvian mechanism would. And conversely, people with very low willingness to pay are people who, on average, just are very poor. They have very high values for money. So again, the allocative mechanism would like to give them more of the good. The same assumptions will tell us that the utilitarian planner actually inverts. So the utilitarian planner might want to give less of the good to low willingness to pay. And why is that? Because by doing that, they can collect more money, the standard sort of Myasonian idea, of, or the standard screening idea of by screening out low types, you can raise more revenue from high types. And the utilitarian planner says, that's great because I can then distribute that money among people and I value that more. And conversely, the utilitarian planner would like to give, for similar reasons, the utilitarian planner would like to give high types, high willingness to pay types, more of the good than the Pigouvian tax would, because again, this can generate more money for us to give out. So the allocative efficient planner and the utilitarian planner sort of would rotate, not fully rotate. We only have very weak results here, but nevertheless would distort relative to the Pigouvian tax in qualitatively opposite directions. And in general, uh, that's all there is to it. So a linear tax on consumption is optimal if and only if these virtual values are linear. And these virtual values under non-degenerate distributions are not going to be linear. So regardless of alpha, regardless of how much the planner cares about allocative or utilitarian preferences, if you're actually going to do this, the planner will use a nonlinear tax, and the outcomes will not be Pareto efficient. So you'll be giving up Pareto efficiency in order to score better on these objectives that you care about. I wanted to show you a little bit on how tractable these functional forms are, some functional forms are in this model. So for instance, suppose the value for the good and money are jointly log normally distributed. So this is the joint log normal distribution. We allow for a correlation coefficient between the value for money and the good. And this sort of specific thing over here is just to make sure that the average distribution, the expectation of theta t is 1, as we assumed. So you can calculate all these terms. They all have nice closed forms under the log normal distribution. And you get this perfectly interpretable virtual value that is just a function of the parameters, the few parameters that you have in a joint log normal distribution. It just depends on this parameter beta, and the beta is just the covariance of theta v and willingness to pay divided by the standard deviation, the variance of willingness to pay. So these things are all calculatable in closed form. And with that sort of thing, with this, you can actually get very clean comparative statics. So for instance, suppose beta is negative, that is to say the covariance of theta v and willingness to pay is negative. Then you can get you can find a level of disutility such that if the cost of the externality is larger than this level of disutility, then the optimal mechanism is prohibition. And if it's smaller, then the optimal mechanism allocates a fixed consumption quota. That is, so this is just an example of how you can get in clean closed form. You can understand exactly how the joint distribution affects the optimal outcome, and you can derive in closed form that the optimal mechanism takes certain forms. For example, prohibition could be the optimal mechanism, or equivalently, you could get something like a quota as the optimal mechanism. So this is just to illustrate that this thing is very clean. All right. I have about 10-ish minutes, and y'all have been very quiet, so I'll continue speeding along, and then we'll have time for questions. All right. So we wanted to embed this model in a richer, more standard public finance style model. So now we're going to think of each agent as described by 3 components. There's still going to be a willingness to pay for consumption of the good eta rho. There's still going to be a willingness to pay to reduce the externality eta d. And now there's going to be a productivity, which I'll call eta pi. There's going to be an agent of type eta. And this agent, when they consume X and earn an income I, and if they have a net wealth W, they're going to get an overall utility that is given by this. So let's just open this up for a second. They get their willingness to pay for consumption times this V of X function. That's their value for the good. They get the value of their wealth, whatever net wealth that they have. They get disutility from the externality, and they get disutility from earning income, where this disutility from earning income is lower for people with higher productivity. If you're more productive, you can make the same amount of income for less disutility. So this is still a linear form, but it's now inside a standard concave utility function, and income and wealth are endogenous. So what are we going to do? We're going to assume that there are two taxes. One we'll call the income tax. That's a tax that depends only on your income. The other is a sales tax. That's a tax that depends only on the amount you consume. And now, what is the agent going to do? They're going to take they're going to learn what is the income tax in society, what is the commodity tax in society. They're going to choose how much income to produce, and they're going to choose how much of the good to consume. Given how much income they produce, they're going to pay an income tax. Given how much good they chose to consume, they're also going to pay an amount to consume that good. They're going to enjoy a wealth equal to all the money they have left over. They're going to get a utility from consumption, and they're also going to get a disutility from the externality in society. So this is the agent's maximization problem. And sorry, this should have been, this is max actually. And this is the maximal value that this agent can get. This is the value function for the agent, which is an agent of type eta faced with sales tax T and income tax T tilde will get this value in society. So what is the planner's problem? The planner's problem can basically be written as this planner is going to take a arbitrarily given income tax as fixed, and it's going to say to itself, okay, let's maximize the total utility with some given welfare weights G. So standard utilitarian, for example, would just be that G is 1. All right. What is the what are our results in this setting? The main result is that you can take this you can take this nonlinear problem over here, which is this bilevel problem where you choose T, and then given T, each agent gets this value function. You can solve that problem, or any solution to that problem must also solve a standard linear problem. What linear problem must it solve? It must solve this linear problem where theta star T, the value of money associated with a type eta, is just their marginal social welfare weight G eta times their marginal utility at the optimal. So if you could, if you knew what these so one way to put it is at the optimal to this, you can compute these things. You can compute this thing, and now you must also have solved the linear problem at these weights. A different way to put it is if someone just gave you these weights, you could have solved the linear problem originally. And why is that useful? Because it means that all the characterizations we had going before at these optimal, at these endogenously determined welfare weights, at these optimal endogenously determined value for money, that characterization still continues to hold. So this value for money is endogenously determined, but all our results from before continue to fall over. So that means that our previous characterizations of optimal utilitarian taxes, our characterization of Pigouvian taxation for the quasi-linear case, all of that translates to this more general case where the agent's income is endogenous, they're subject to an arbitrary income tax, and utilities are non-quasi-linear. Okay? Like I said, this has implications on Atkinson and Stiglitz. So Atkinson and Stiglitz show that if the good does not exhibit an externality and all agents have the same preference over consumption, the optimal commodity tax is 0, and a utilitarian planner can solely rely on income taxes for redistribution. In our setting, we show that basically both of these conditions, that is no externality and identical preferences, are necessary for 0 commodity taxes to be optimal. So suppose G, the marginal welfare weights are 1, then a 0 commodity tax is optimal if and only if theta d is equal to eta d is equal to 0. So if and only if you have no externality, and the distribution of eta rho, the value for money, the willingness to pay, is degenerate. Okay. So in any other circumstance than these two, you do want to do commodity taxation. All right. The final thing we do in this paper is we actually take this to, well, we don't take this to data as much as we just calibrate this in a very simple model just to show you like some of the implications. This isn't meant to be like the final word. Like we would love to sort of flesh this out into a full empirical project, but we need better data for this. But airline travel is kind of economically important. We know that lots of countries and organizations are concerned about both the quantity of emissions and the type of emissions that are caused by air travel and how to regulate it. And there's lots of different proposals. So, for example, Greenpeace wants to put a frequent flyer levy, which is to say that your first round trip is free, but then afterwards you pay more and more for every flight that you take. And conversely, like the Green Party of Norway wants to just put a tax saying no one can fly more than 10 trips a year. Another nice thing about airline taxation is that nonlinear taxes are implementable here in practice because you have to give your ID every time you fly. You can, in principle, then get a bill at the end of the year, which is to say you flew 18 flights this year. This is the additional amount you have to pay. That might be difficult in the context of something like gasoline taxation, where you don't show your ID every time you refill your car. So we're going to calibrate this model for in the special case or under the sort of functional form assumption that our agent's value for flying and value for money is log normally distributed, the model that I showed you before. We're going to use welfare weights of the form I to the minus gamma. So we're roughly going to say that the planner is indifferent has some redistributive preference, and that redistributive preference is roughly that they are indifferent between taking $2 from a household making 100K and $1 to one making 10K. We're going to assume that the household income is log normally distributed. That's not the worst assumption. It does kind of badly here, but you can calibrate, sort of visually, it's not the worst thing for household incomes to assume that they're log normally distributed. We'll assume that, what is this? We will assume that the marginal value of an additional trip is this power form, which is a constant elasticity assumption. And this constant elasticity, we just plug that down to this number that we found in a paper. Again, all of this can be read. Okay. So you can take this and you can, given the values for the good and so on, you can calculate what is a calibrated number of round trips by household. And you can also, we have by household a number of round trips. We also know sort of a distribution. We know sort of marginal distributions of number of round trips household take and the marginal distribution of incomes. So we calculate and we have this sort of survey data, which is how many flights did you take as a function of your income. So we dump that all into a sort of calibration exercise to figure out the best fitting joint distribution. And this is the best fitting joint distribution. So this is how much, given the best fitting joint distribution, this is the real and calibrated number of trips by household. This is the distribution of that. And you can then, we then take an assumption that every, the sort of Pigouvian, like the associated greenhouse gases and so on, we assume that if that, the Pigouvian tax for that was $50 per flight, which was roughly what we found in some papers, this should be the utilitarian taxes per flight, and this should be the allocative efficient taxes per flight. So what's the story here? The utilitarian will charge a high number for the first round trip and then charge a decreasing marginal tax for every additional round trip that you take. The story being similar to what we said in these qualitative differences, which is to say that the utilitarian will want to cause some poor people who might have flown a little bit to instead opt out, and because they do that, you can actually extract a lot more money from richer people and redistribute that, which the utilitarian planner is happy with. Conversely, the allocative planner says, no, that's not right. Poor people or people who fly very little, not because they have low willingness to pay, but because they just have very little money. You don't want to misallocate it by that much. So instead, you have a very low tax on the first round trip, and then you increase it steadily afterwards. You can see the corresponding counterfactual numbers of trips. So this is the average, this is the fraction of society that takes 0 trips in the fitted model, and this is how much they would take under the Pigouvian. What fraction of society would take 0 trips under Pigouvian, allocative, and utilitarian, and so on and so forth for other numbers of trips. So this is a very basic calibration. The main thing was that under very reasonable assumption, you get that the utilitarian and the allocative would give you different shapes, increasing versus decreasing for your margin for the marginal tax per flight. All right.
Mallesh,
Yes.
one quick question. But this also looks like that for some small alpha, you actually almost get a linear tax again, right? If you just somewhere in between the two.
Yeah, it won't be. I mean, it looks like it, but it won't. The theorem tells us that it won't.
Okay.
So you'll never get a linear. It just won't equal out. These are the average rebates under the various models, and like I said, we started with this Pigouvian will pay $50 per flight. That was the assumption. So both allocative and utilitarian will charge a lot more. All right. So that's sort of, I'm close to out of time, and I'd love some time to chat if there are questions. But that was the paper. As I said before, sort of Pigouvian taxes, which we like as economists, they favor the rich, but we show sort of how you might interpret it that way. And utilitarianism encodes a preference for redistribution. So we propose this other objective, allocative efficiency. Both allocative and utilitarian optimality will lead to Pareto-dominated outcomes. So you can't allow resale of the good. It has to be something linked to you. So for example, airline taxation is something that is feasible, or congestion pricing where it's linked to your car is feasible. The optimal taxes are nonlinear and may not be in general are not equal to what you would get from a first order approach, even under very natural regularity assumptions. The utilitarian and allocative objectives distort differently, distort the Pigouvian differently. And we have sort of rich functional forms and a bunch of sort of implications. So that's the paper.